China is building a 100-kilometer particle accelerator, and it could change physics forever. That's a ring so vast it would wrap around the entire city of Paris nearly 3 times. You heard that right, 3 times around one of the most iconic cities on Earth, buried underground. This machine isn't just the biggest of its kind ever built, it's a calculated move that reaches far beyond physics. And by the end of this, you'll understand exactly why. But first, what is this thing? And what is China actually trying to do? The machine that shouldn't be possible. Most people have never heard of the CEPC, and that's exactly the point. While the world has been focused on AI, space races, and semiconductor wars, China has been quietly designing something that most physicists thought wouldn't exist for another generation. A particle accelerator so large, so precise, and so powerful that it makes the current world record holder look like a prototype. That record holder is CERN's Large Hadron Collider, the machine that discovered the Higgs boson in 2012. A machine that took decades to build, spans the border of 2 countries, and cost over $5 billion. The LHC sits in a tunnel 27 kilometers around. Scientists celebrated it as one of the greatest engineering achievements in human history. China's machine would be 100 kilometers around, nearly 4 times the size. But here's what most people don't realize. Bigger isn't just about bragging rights. Bigger, in particle physics, means something that changes everything. When you collide particles inside a circular accelerator, the particles lose energy as they curve around the ring. The tighter the curve, the more energy you lose. That's just physics, you can't argue with it. But if you make the ring larger, the curve becomes gentler. The particles hold their energy longer. And that means you can collide them with a precision that a smaller machine simply cannot achieve. The CEPC, the Circular Electron Positron Collider, is designed to do something very specific. It's not built to smash protons together with brute force like the LHC. It's built to collide electrons with their antimatter counterparts, positrons, in a controlled, ultra-clean environment. And it's engineered to do this at one precise energy level. The exact energy level at which one particle, above all others, is produced in enormous quantities. The Higgs boson. You've probably heard the name. Maybe you've heard it called the God particle, a nickname that physicists hate, by the way. But that's stuck because the Higgs boson is the particle responsible for something almost incomprehensible. Mass. The reason matter has weight. The reason you don't just drift through the universe as a cloud of weightless energy. The Higgs boson is the messenger of the field that gives everything in existence its substance. And we only discovered it 13 years ago. Here's where it gets unsettling. We found it, but we barely understand it. The LHC detected it, confirmed it existed. But the way the LHC works, Higgs bosons get produced inside an incredibly messy environment. Protons smashing into protons, debris flying everywhere, signals buried in noise. It's like trying to study a whisper in the middle of a thunderstorm. The CEPC would be the silence after the storm. In a 100-kilometer ring, colliding electrons and positrons produces Higgs bosons cleanly, precisely, with almost no background noise. Scientists estimate it would generate over 1 million Higgs bosons per year. That's not a modest improvement on what the LHC does. That is a fundamentally different category of machine, a dedicated Higgs factory, the most powerful one ever conceived. And what you could learn from studying 1 million clean Higgs bosons per year might not just refine our understanding of physics. It might break it entirely. But before any of that science can happen, China has to actually build this thing. And when you look at what that requires, what engineering problems have to be solved just to make this machine exist, you start to realize that this project was never only about physics. Building the impossible. So, how do you actually build something like this? Because a 100-kilometer particle accelerator doesn't just require a big hole in the ground. It requires you to solve engineering problems that have never been solved at this scale before. Problems that push the absolute limits of what human beings know how to do. And here's what most people don't realize. Every single one of those problems forces China to develop capabilities it currently doesn't fully have. That's not a coincidence. That's the point. Let's start underground. The tunnel itself needs to be 6 meters wide and 5 meters tall, carved through rock for 100 kilometers. That's not a subway line, that's a city. A hollow city buried 300 feet beneath the surface, precision bored to millimeter tolerances, because even the slightest deviation in the tunnel's path throws the entire machine off. The civil engineering challenge alone would rank among the most ambitious construction projects in human history. But the tunnel is just the beginning. Inside that tunnel, you need magnets, thousands of them. Around 4,360 dipole magnets, each one roughly 49 feet long, lining the inside of the ring to bend the particle beams around the curve. And these aren't ordinary magnets. They're superconducting magnets, meaning they have to be cooled to temperatures close to absolute zero, -452 degrees Fahrenheit, to carry electrical current without any resistance whatsoever. Think about what that means. You need to cool 65 kilometers worth of magnets to a temperature colder than outer space. And you need to hold them there, continuously, for years of operation. The cryogenic infrastructure required to do that is almost incomprehensible. Hundreds of kilometers of insulated pipework, massive refrigeration plants stationed at intervals around the ring, liquid helium flowing through the system around the clock. If one section warms up unexpectedly, a phenomenon called a quench, the energy stored in those magnets releases in an instant. The result is an explosive failure that can destroy equipment worth hundreds of millions of dollars. But even that wasn't the biggest problem the engineers faced. The beam pipe, the tube through which the particles actually travel, has to be emptier than outer space. Not almost empty, emptier than the void between planets. Because if a single particle in the beam strikes even one stray gas molecule, it scatters. The beam destabilizes. Years of preparation, wasted in a fraction of a second. Maintaining that level of vacuum across 100 kilometers of pipe is, by itself, a feat of engineering that has never been attempted at this scale. And here's what makes all of this almost unbearable in its complexity. These systems don't operate in isolation. They operate simultaneously. The cryogenics, the vacuum, the magnets, the beam, all of it running at once, across 100 kilometers, for years without interruption. If the cryogenic system hiccups in one section, the magnets in that segment warm up. If the magnets lose their field, the beam drifts. If the beam drifts, it hits the pipe wall. And if it hits the pipe wall at near light speed, the energy release can damage equipment that took years to manufacture and install. Every subsystem depends on every other subsystem. It's not engineering one machine, it's engineering an ecosystem, one where a failure anywhere can cascade into a catastrophe everywhere. And then comes perhaps the most quietly astonishing challenge of all. The particles racing around that ring aren't just fast. They're moving at 99.9% the speed of light, and they have to stay on a path accurate to the width of a human hair. For 100 kilometers, continuously. That requires thousands of precision alignment systems, nanometer-scale sensors, and real-time correction mechanisms firing thousands of times per second to keep the beam from drifting by even a fraction of a millimeter. This is where it starts to get interesting. Because mastering nanometer-scale precision, knowing how to measure, correct, and control physical systems at that level of accuracy, isn't just useful for particle physics. It's exactly the kind of capability that sits at the heart of making advanced semiconductor chips. But before we get there, let's talk about what this machine is actually going to find. What you could actually discover. Here's what no one tells you about the Higgs boson. Finding it was extraordinary. But finding it was just the beginning. What physicists actually need, what they've been desperate for since 2012, is to study it deeply, repeatedly, under controlled conditions clean enough to catch the tiniest deviations in how it behaves. Because here's the thing. Our best theory of physics, the Standard Model, is one of the most successful scientific frameworks ever constructed. It has predicted experimental results with stunning accuracy for decades. But physicists know it's incomplete. dark matter exists, and the standard model can't explain it. The universe is made of matter rather than antimatter, and the standard model can't explain that either. There are forces and phenomena out there that our best equations simply don't account for, and the Higgs boson might be the key that unlocks all of it. Here's why. The standard model makes very precise predictions about how the Higgs should interact with other particles, what physicists call its couplings. If you measure those couplings carefully enough, and you find that they deviate even slightly from what the standard model predicts, that deviation is a fingerprint, a signal, evidence of something new, something the theory missed. The LHC can measure Higgs couplings to around 5% accuracy. That sounds precise. But in the world of fundamental physics, 5% is the difference between confirming a theory and missing a revolution entirely. The CEPC would push that precision down to a fraction of a percent. That's not an incremental improvement. That's a completely different level of sensitivity. The kind of sensitivity that could reveal hidden forces, new particles, or entirely new layers of reality that have been invisible to every instrument ever built. Think about what that actually means for a moment. Dark matter makes up roughly 85% of all the matter in the universe. You can't see it, you can't touch it. Every galaxy we've ever observed is shaped by it, and we have no idea what it is, not even close. If the Higgs boson couples to dark matter in some hidden way, a way that only shows up at a fraction of a percent level of precision, the CEPC would be the first machine sensitive enough to catch that signal. The same goes for the profound mystery of why the universe is made of matter at all, and not equal parts matter and antimatter that canceled each other out at the beginning of time. These aren't abstract academic puzzles. They are the deepest unanswered questions in the history of science, and the CEPC might be the key that finally opens them. But this was just the beginning of what the CEPC could achieve. Because after its first decade of operation as a Higgs factory, the plan doesn't stop. The same 100-kilometer tunnel gets upgraded, new magnets go in, and China switches on the Superconducting Proton Collider, the SPPC, a machine that would collide protons at energies roughly 7 times greater than the LHC. That's not a follow-up project. That's a century-long physics program, a roadmap that would keep China at the frontier of fundamental science for generations. The physics alone would justify the price tag. But the physics is only half the story, because what China is really building, the capability that nobody is talking about, runs much deeper than particle collisions. And it has everything to do with the chips inside your phone. The hidden layer chips, X-rays, and the real game. This is the part nobody is talking about. Because when you look at the CEPC, really look at it, you start to notice something. Every single engineering challenge required to build this machine maps almost perfectly onto the capabilities needed to compete in advanced semiconductor manufacturing, and that is not a coincidence. Let's go through it. Start with the accelerator itself. When electrons race around a circular ring at near light speed, they naturally emit radiation as they curve powerful beams of X-rays. Physicists call this synchrotron radiation. For decades, it was considered a nuisance, an energy loss problem to be managed. Then scientists realized those X-rays were extraordinarily useful. Because synchrotron X-rays are so intense, so precise, and so tunable that they can illuminate the atomic structure of materials in ways nothing else can. And here's the connection that should make you sit up straight. High-precision synchrotron X-ray analysis is one of the most important tools in advanced semiconductor research. It lets scientists examine crystal defects in silicon wafers at the atomic level. It reveals exactly where impurities are hiding inside a chip substrate. It maps the internal stress patterns in semiconductor materials that determine whether a chip performs at its best or fails. China's existing synchrotron facilities already do this work. A machine the size of the CEPC would generate X-ray beams of an entirely different magnitude, more powerful, more precise, more capable of unlocking semiconductor materials science at a level that simply isn't possible today. But this was just the beginning. Remember those nanometer-scale beam control systems from Chapter 2? The sensors and alignment tools that keep particles on a path the width of a human hair across 100 kilometers? Those same precision measurement technologies, developed, refined, and mass-produced for the CEPC, translate directly into the metrology tools used inside advanced chip fabs. The instruments that measure whether a transistor gate is the right size. The tools that check whether a pattern has been etched with sufficient accuracy onto a silicon wafer. In chip manufacturing at the 2-nanometer node and beyond, the tolerances are so extreme that even a single misaligned atom in the wrong place means a defective chip. Mastering measurement at that scale requires exactly the kind of capability that building a 100-kilometer accelerator forces you to develop. Then there's the material science layer. Building the CEPC requires China to develop new generations of superconducting materials, ultra-pure metals, and exotic alloys that can survive extreme cold, intense radiation, and years of continuous operation without degradation. Many of these same material properties, purity, structural consistency, thermal stability, are exactly what next-generation semiconductor substrates demand. The R&D pipeline that feeds the collider feeds the chip industry too. You can't separate them. And then came the most overlooked connection of all. The CEPC will generate petabytes of collision data every single year. Processing that data requires custom high-performance computing architectures, AI-driven analysis pipelines, and simulation software of extraordinary sophistication. Building those systems trains Chinese engineers in exactly the kind of chip-level optimization and high-performance computing design that underpins modern semiconductor innovation. The machine doesn't just use chips building the infrastructure to run, it makes better ones possible. Step back for a moment and look at the full picture. Synchrotron X-ray tools for atomic-level materials analysis, nanometer precision measurement systems, advanced superconducting material development, high-performance computing expertise built from the ground up. Every one of these capabilities feeds directly into what China needs to close the gap in advanced chip manufacturing. Every single one. This isn't a particle physics project with semiconductor benefits on the side. It's a vertically integrated scientific infrastructure program, and the Higgs boson is almost a bonus. But none of this happens in a vacuum. There's a reason China is building this now. And to understand that, you need to understand the world it's being built into. Why China? Why now? To understand why China is building this machine, you need to understand the world it's being built into. In October 2022, the United States government made a decision that sent shockwaves through every boardroom and government ministry in Beijing. It imposed sweeping export controls on advanced semiconductors and the equipment used to make them, and not just on chips. On the knowledge, the tools, the people, and the supply chains that produce them. The crown jewel of those restrictions was ASML, a Dutch company. The only company on Earth capable of manufacturing the extreme ultraviolet lithography machines needed to produce chips at the most advanced nodes, 2 nanometers and below. The machines that make the chips that power artificial intelligence. The machines that China cannot buy. Then came the most devastating blow of all. In 2023, the Dutch government under US pressure revoked ASML's export licenses to China entirely. The door didn't close slowly. It slammed shut. And overnight, China's path to the most advanced chips in the world became a wall. For most countries, that would be the end of the story. But China wasn't done. Because here's what the export controls actually did beyond their intended effect. They forced China to ask a question that no country had ever been forced to ask quite so urgently. What if we didn't need their tools at all? What if we built the foundational science and technology infrastructure so deep, so self-sufficient, that we could develop the tools ourselves from the ground up? That's the CEPC. It's not the only answer China is pursuing. Tsinghua University researchers are developing particle accelerator-based EUV light sources that could bypass ASML's technology entirely. Chinese synchrotron facilities are already being used for semiconductor materials research. The country has been systematically building every layer of scientific infrastructure it needs. The CEPC is the most ambitious piece of that puzzle and the most overlooked. There's a historical echo here that's impossible to ignore. CERN was built in the aftermath of World War II, partly as a scientific project, but also as a deliberate strategy to rebuild European scientific prestige and industrial capability. The technologies that emerged from CERN, the World Wide Web, advanced materials, medical imaging breakthroughs gave Europe decades of scientific and industrial influence that had nothing to do with particle physics. China has studied that history carefully, and it has decided that if you can't buy the tools that define the future, you build the science that makes those tools possible. But not everyone agrees this is the right bet to make. The reckoning and what it means anyway. Here's the part that nobody expected. The CEPC was not included in China's 15th five-year plan, the plan that runs from 2026 to 2030, the very window in which construction was supposed to begin. No funding commitment, no green light, just silence, and a price tag that even the world's second-largest economy blinked at. Early cost estimates for the CEPC alone ranged from $5 to $10 billion. But as the design grew more ambitious and the full CEPC-SPPC program was factored in, internal projections climbed to $20 billion or more, spread across decades of construction, operation, and upgrades. And unlike a high-speed rail line or a semiconductor factory, a particle accelerator doesn't generate revenue, it generates knowledge. And right now, Beijing is being asked to choose between knowledge and everything else competing for that money. The critics made their case loudly. A Nobel Prize-winning Chinese-American physicist, Chen-Ning Yang, publicly argued that billions would be better spent on social needs hospitals, pensions, housing for the hundreds of millions of people whose lives haven't yet caught up with China's economic miracle. On social media, the debate turned raw. Young people asked why the state could fund a ring in the ground but not affordable apartments in the cities where they were trying to build a life. And here's the uncomfortable truth. That argument isn't wrong. But here's the counter-argument that history keeps proving right. CERN was considered a luxury too. The World Wide Web, the infrastructure that every human being with a smartphone uses every single day, was invented at CERN as a tool for sharing physics data. MRI machines that diagnose cancer in hospitals around the world emerged from accelerator magnet technology. Proton therapy, one of the most precise cancer treatments ever developed, grew directly from particle physics research. None of that was planned. None of it was predicted. That's precisely the point. The United States learned this lesson the hard way. In 1993, Congress canceled the superconducting Collider, a machine with an 87-kilometer ring being built in Texas after spending $2 billion on it. Physicists called it one of the most damaging science policy decisions in American history. Within 2 decades, Europe's LHC had discovered the Higgs boson, and the center of gravity in particle physics had shifted across the Atlantic permanently. China knows that story. Every physicist in Beijing knows that story. And this is where the pause becomes more interesting than a cancellation ever could, because the CEPC hasn't been killed. The research groups are still working. The prototype components are still being built and tested. The engineering design report is still being completed. What China appears to be doing is exactly what a strategic power does when the timing isn't right. It keeps the engine warm without committing to the launch. The question isn't whether China will build this machine. The question is what the world looks like when it does.